The interpretation of the National Electrical Code, specifically regarding Article 250.54, which addresses supplementary grounding electrodes, is important. The provision stating the earth shall not be used as the sole equipment grounding conductor is key, and the understanding that it should refer to the earth as the sole equipment grounding electrode is correct. This interpretation is consistent with the fundamental principles of electrical safety and grounding practices. The 2005 National Electrical Code maintains this principle in Article 250.54. The core reason behind this regulation lies in the inherent unreliability of the earth as a conductor of electricity. The earth's resistance is highly variable, subject to a multitude of factors that render it unsuitable as the sole path for fault current. These factors include, but are not limited to, soil composition, which can range from highly conductive clay to poorly conductive sandy soils. Moisture content plays a significant role, with saturated soil offering low resistance compared to dry soil. Temperature variations can also affect soil resistivity, as can the presence of minerals and chemicals. Furthermore, the depth of the earth electrode and its contact area with the soil influence the overall grounding resistance. Because of these variables, relying solely on the earth for grounding presents an unacceptable risk. The primary purpose of a grounding system is to provide a low impedance path for fault current to return to the source, thereby facilitating the rapid operation of overcurrent protective devices such as circuit breakers or fuses. If the earth's resistance is too high, the fault current may be limited, preventing the overcurrent device from tripping quickly enough to prevent damage or injury. The delayed or absent tripping of overcurrent protection, in scenarios where the earth is the only grounding means, can lead to hazardous voltage potentials on equipment enclosures, increasing the risk of electric shock to personnel. It can also result in equipment damage due to prolonged exposure to fault currents. To mitigate these risks, the National Electrical Code mandates the use of supplementary grounding electrodes in conjunction with the earth. These electrodes serve to create a more reliable and consistent grounding path, minimizing the reliance on the variable conductivity of the earth itself. Acceptable supplementary grounding electrodes include driven ground rods, buried ground plates, and other conductive objects specifically designed for grounding purposes and in direct contact with the earth. These electrodes, when properly installed and connected, provide a low impedance path for fault current, ensuring the prompt operation of overcurrent protective devices and minimizing the risk of electrical hazards. Ground rods are typically made of copper or copper-clad steel and are driven vertically into the ground. The length and diameter of the rod, as well as the number of rods used, are determined by the required grounding resistance and local soil conditions. Ground plates are typically made of copper or galvanized steel and are buried horizontally in the ground. The size and shape of the plate, as well as the depth of burial, are determined by the required grounding resistance and local soil conditions. Other types of grounding electrodes may include metallic water pipes, metal building frames, and concrete encased electrodes. The selection of the appropriate type of grounding electrode depends on the specific application and the available site conditions. It is important to note that the National Electrical Code specifies requirements for the installation and connection of grounding electrodes to ensure their effectiveness. These requirements include minimum burial depth spacing between electrodes, and the use of approved grounding connectors and conductors. Furthermore, the National Electrical Code requires that the grounding system be tested periodically to verify its effectiveness. This testing typically involves measuring the grounding resistance using specialized equipment and comparing the results to acceptable limits. If the grounding resistance is found to be too high, corrective actions must be taken to improve the grounding system. These actions may include adding additional grounding electrodes, improving the soil conductivity, or repairing any damaged or corroded grounding connections. In addition to the requirements for supplementary grounding electrodes, the National Electrical Code also addresses the bonding of metallic equipment enclosures and other conductive parts of the electrical system. Bonding is the process of connecting these parts together to create a low impedance path for fault current. Proper bonding helps to ensure that all metallic parts of the electrical system are at the same potential, minimizing the risk of electric shock. The National Electrical Code specifies requirements for the size and type of bonding conductors, as well as the methods of connection. It also requires that bonding connections be made in a manner that is permanent and reliable. The proper installation and maintenance of a grounding and bonding system are essential for electrical safety. A well-designed and properly installed system can help to prevent electric shock, reduce the risk of fire, and protect equipment from damage. It is important to consult with a qualified electrical contractor or engineer to ensure that the grounding and bonding system meets the requirements of the National Electrical Code and local regulations. In summary, while the earth plays a role in the overall grounding system, it cannot be relied upon as the sole equipment grounding electrode due to its variable and unpredictable resistance. Supplementary grounding electrodes are required to provide a more reliable and consistent path for fault current, ensuring the safety and proper operation of the electrical system. These electrodes, in conjunction with proper bonding techniques, create a comprehensive grounding and bonding system that minimizes the risk of electrical hazards. The National Electrical Code provides detailed requirements for the design, installation, and testing of grounding and bonding systems to ensure their effectiveness.